Welcome to my Finagle for Beginners talk. The quick reminder, please rate the app. I'm happy for constructive feedback to improve this talk even more. What I want to talk about today is how to build a distributed system with Finagle. First, about me. I'm Muki. I'm a Scala developer at Gute Frage, and some of you may know me as one of the native packager maintainers. So first of all, who of you have heard about Finagle before? That's cool. So a very brief introduction. Finagle is an extensible RPC, remote procedure call system for the JVM, used to construct high concurrency servers. So yesterday there was a nice talk from Petra about gRPC, and today we heard something about Lagom, and Finagle is just another alternative for constructing microservices. And the special thing about Finagle is most of the Finagle code is protocol agnostic, simplifying the implementation of new protocols. So for instance, Finagle ships with protocol HTTP, Thrift, Thrift MUX, Memcached, MySQL, and Redis. So you can build with the same abstraction, you can use different protocols. The reason why I'm standing here today, at Gute Frage, we're using Finagle now for more than 4 years, but many of the early developers aren't here anymore. So we're trying to rebuild some of that knowledge. And the Finagle documentation is in a lot of places incomplete. And this is where we try to give back something to the community by writing documentation, writing blog posts, and giving this talk. So sharing information about Finagle and how to get started, because that's really hard if you're new to Finagle and simply want to try it out. So the best thing to learn something is to build something. I apologize that I won't show any live coding or running the system because it would take too much time switching all over again. And I want to show you some of the more deeper concepts of Finagle that really improve the usage of Finagle and your day-to-day life. So the weather system we're building today consists of a server that stores temperature data. There's a sensor that will generate this data and send it to the server. We will also provide an HTTP API that reads the aggregated data from the server and provides an HTTP endpoint. And we will use Zookeeper for service discovery. So we will talk about Zookeeper and how these things work together in more detail. But this is a big picture of what this talk will build today. So before going into the Finagle service details, I want to talk about Finagle util because there's not much documentation of the utils, but it's highly recommended to use a lot of the features provided by utils. And the two concepts or the two features Finagle util provides I want to show you are the app trait and flags. So Finagle comes with its own app trait. It's in com twitter app.app. It's more or less like the Scala app trait, but it provides a lot of helper functions. For instance, you have lifecycle methods like pre-main. In this case, we initialize some Dtabs. We will talk about that later. You have an on-exit, and you implement an actual main method. In this case, we start a server, and we say when the service got shut down, no matter how, we want to close it. And so you get some nice helper functions, and there's also Twitter server, which builds up on the app trait, which provides you a nice admin interface. So make sure to check that out as well. The other thing are flags, and they are the abstraction from Finagle to provide command line parsing. You define flags like this. If you use the app trait, you have a flag method in scope that you can simply call. A first parameter is the name, then you specify a default parameter and a description. And as you can see, flag takes a type parameter, so which type has the flag you're parsing. And as you can see, the second one, env, it looks like a custom type. And how to provide the parsing for these kind of CLI flags? Well, Finagle provides a type class for it. It's called flaggable. You implement the type class for a specific type, how to parse a string into an env, and you're good to go. So these two basic concepts are used everywhere in Finagle, but they are not mentioned anywhere as far as I'm concerned. So you should know them. The second thing is Thrift. So I mentioned it in the beginning. Finagle is protocol agnostic and provides several protocols. We will use Thrift as a protocol for inter-service communication. And Finagle provides a lot of tooling around Thrift. First of all, a small introduction to Thrift. It's a cross-language service development framework. I think it was initially started by Facebook. It's similar to Protobuf, compared. It provides a lot of code generation for various languages, and Finagle provides a very good integration with it. We will see a lot of the implementation details later on. And you can describe your API in a language agnostic way. And I can't stretch this enough. Petra yesterday gave the best practice to share your API definitions in a compiled package. We at Gute Frage do this as well, but we also ship the Thrift files as well, so we can inspect the Thrift definitions afterwards as well. And the API, well, is contained in a single package. So what does a Thrift file look like? For service definition, you start with a namespace. The wildcard, you could specify different languages. For different languages, different namespaces. For instance, Java or Scala. But as we don't care, we simply use a wildcard. And then you give, it's like a package name. Like it's net gute Frage temperature.thrift. So every code that gets generated will be put in this package. Then you have a basic construct. It's called struct. Basically, it maps to case classes in the end, right, what you get out. So we define temperature datum here, so a single data point, which contains of an integer of Celsius, and a long, which is a UTC timestamp. And for service definitions, you use the service keyword, a temperature server, and then it's almost reads like Java, like abstract Java definitions. So you have the return type, which is for the add method, it's void, then you have the name, and then you have a parameter list. Optionally, you can specify throws declarations if your service throws any exceptions, and that's basically it. So this is how we define all our Thrift definitions. You can also import other definitions. So if you have a shared model in your service, you can import other definitions. But besides that, the language is pretty simple. So Scrooge is the Thrift compiler provided by Finagle. Well, it's a separate library, but it's built up to work with Finagle. And it generates the Scala codecs for Thrift, so you can decode and encode your messages. It generates client and server adapters, so you can implement a server, a service you specified, and you can spawn clients from the generated stubs. And it provides a nice SPT plugin, so you can just integrate it in your build plugin. And since the recent versions, you simply add the plugin to your build plugins SPT, and the auto plugin will be automatically enabled. And everything you put in source mains Thrift will be used to generate Thrift codecs, Scala, the Scala code. Okay. So now we get into the more conceptual details of Finagle, and it's based on a paper called Server as a Function, and it explains 3 concepts. So the first concepts are futures. I guess you're all familiar with that. They are a way for a container for asynchronous computation. Finagle rolls its own implementation of futures. There are some reasons. One of them was they need cancellation of futures, and another thing you should be aware of, they behave quite differently from Scala futures. So when you have a Scala future and you create it, it will always run on the specified execution context, while Finagle features are simply containers for values. You have to specifically run them on an execution pool to really make them asynchronous. Then we have filters. Unfortunately, I won't have time to talk about filters a lot today, but they're a way to put general logic in your request response chain, for instance, success logging. And then we have services, and this is one of the main abstractions from Finagle. They describe system boundaries. System boundaries are represented by asynchronous functions called services. They provide a symmetric and uniform API. The same abstraction represents both clients and servers. And this abstraction is pretty straightforward. So you have two types, request and response, and it implements a simple function that maps a request to a future, so an asynchronous result of response. And you can use this to implement your server and to spawn a client to make requests. So how does this look like? The most basic example that comes to mind for everybody is HTTP. So first we have some imports. We import the HTTP protocol and the service definition, and then some helpers to start up the server and spawn the futures. And this is what a very basic service implementation looks like. So we say we want a new service, which is nothing else than a function. So we implement the apply method, which takes an HTTP request, and we return simply a future value with HTTP response. And as you can see right here, Finagle is by design very low level because it's built to it should make it easy to build new protocols. So it is based on this layer. And then you start the server by simply calling HTTP, so your protocol.serve, bind it to a specific port, give it the actual service implementation, and it returns back a future that you can wait for until the server is finished. And that's it. So that's the smallest version that you can build a Finagle service in. And the client on the other side, it uses the same abstraction. So you simply spawn a HTTP client by calling HTTP new service, and then you bind it to some host where you want to make your requests to. In this case, we use Scala lang on port 80, and then we send a request and get a future back, and we can call the onSuccess method, and when the response returns, we just print it. And this is the very core concept of Finagle. You always work with these services that take some kind of a request, and you get an asynchronous response. So let's implement the first step of our temperature service. So first, recall the service definition. We saw it earlier. So this is a package, and this is the definition. So we have an add method where we can add single data points, and a method where we can get the mean of the temperature we have seen so far. So we first import the Thrift definitions that were generated by Scrooge. They are all in this package. And then we implement the temperature service.future iphase. And this is some of the parts where I really struggle a lot. How do I implement which stuff? Because Finagle doesn't tell you what to do. But in the end, it's pretty straightforward. So you have you just implement the method we saw before, the service we saw before in the definition, which almost looks the same. The implementation, well, it's up to you how you implement the add and mean. In the example repository, it's just an in-memory storage, right? And this has the type temperature service of future. So there is a more generic version of temperature service where you can plug in any asynchronous container if you like. But for the Thrift support, it expects the future iphase definition, not a generic temperature service. So this hasn't the right shape to be a service because a service is a function from request to some response. And Thrift is a binary protocol. So we generated with this helper method also generated by Scrooge, and we create a Finagle service, which has the shape of array byte and the response is again, it's binary, an array of bytes. And we plug in the service, and we specify the protocol that Thrift should use to encode and decode the messages over the wire. And we use a simple binary protocol. I think there's a compact protocol and a plain text protocol as well, which is nice for debugging if you need that. And then, almost like the HTTP server, we choose our protocol, which in this case we use not Thrift, but Thrift-MUX, which is an optimized implementation of the Thrift protocol by Twitter, because it allows multiplexing on a connection, which is, well, takes less resources and less connections. So I recommend using that. And we want to implement a server. We give it a label. This is nice for debugging later and for monitoring, to give it a proper name. And then we serve and announce it. So serving means starting, and announcing means I make it publicly available that I've started a server somewhere. And you do this by giving the service a name. And name has a very specific syntax, and it's documented in the comment as well. So first you have a schema. Where do I want to announce my service? CK stands for zookeeper. So I say I want to announce myself at some zookeeper instance. Then the second parameter is the host. So there's my zookeeper instance running at port 2181. And then I give it a path. This is where the zookeeper schema knows, well, I will put the information where the server is running under this path. And then there's, in the end, there's a shard ID. And for me, it's still, I don't know what it's for. The documentation just states it's used internally by very few services in our infrastructure. So I think the person who wrote the documentation doesn't know it either, because, well, it's just an artifact somebody added it at some point. So yeah, when I figured out what this is for, I will let you know. And then you give it an address where you want to bind it on your machine, and you give it the service implementation. And this is everything you have to do to implement a basic Finagle service and run it. And it's actually not that much code, but it's not clear from the documentation that it's that easy. And yeah. So we announced it, but now we have to discover it. And this is also an interesting part, because Finagle provides a lot of strategies to resolve your services. We will talk about Zookeeper today, but there are also, you can use DNS or DNS broadcasting. And I think there are 2 or 3 more, but they are not documented anywhere. But if you read the tests of the resolving stuff, you can see what is already provided. So how does Finagle resolve services? The main concept is our names. So every service must have a name. And we've specified the name for our listening server before in the name parameter. And Finagle uses these to identify network locations. And there are two types of name. So there's name.bound, which binds a name to a specific address. And as you can see, it's not only an address, but it's a variable address, because Finagle takes care for you if the address changes. So if your service starts in a new place and announces itself on Zookeeper, these var will make sure that it gets updated accordingly and you use the new address. The other type is name.path, which is a hierarchical path that needs to be resolved to an address. And there's a simple resolver that parses these strings into names. So how does this resolver work? Well, the first implementation we already saw. You give it a schema, bang, and some arguments. And it always resolves to a bound. There are the main 2 resolvers you probably use is Zookeeper that we already saw, and the parameters are the host and the path. And there's the inet resolver. And we already used that in the first HTTP example, where we just put in scalalang.org, port 80, and Finagle by default uses the inet resolver, which simply opens a socket on the given address. But you can, and I would recommend, specify it explicitly if you want to resolve with inet, so people know what you're actually using. And the other strategy are these hierarchical paths, which first resolve to a path, which eventually, after resolving via delegation tables, to a bound. And we will see Dtabs in action later on. But for now, we start with the single schema version, which is static, but easy to get started with. So you create a client, again, by specifying the protocol you want to use, in this case, Thrift MUX. But now we don't want to spawn a server, but a client. So we say .client. And then we want to specify the interface, so the remote procedure interface we want to call. And this is our temperature service, future interface. And we don't specify a name this time, but a destination where the client should look for to resolve this service. And as you can see, it's almost the same as before. It's this time, but this time it's not Zookeeper, but Zookeeper 2. And this is the second mystery for me. There are two implementations, and the Finagle documentation states use Zookeeper 2 resolver for clients and Zookeeper for servers, but there's no explanation why. They both work. I tried out both using Zookeeper 2 resolvers for server and client and the other way around, but they state this, so well, if it works. And so it's the same again. You have the schema, bang, and then your address for Zookeeper, and we put in a label for monitoring. And then you have a simple function from, then you have an instance of your client which implements this feature, and you can just call the functions. So on the client, we just call add and add a temperature datum, and that's it. So this is how you connect services. And under the hood, Finagle manages most of the complexity for you. We're using it for almost 4 years, and we were really surprised about the maturity of Finagle, so we never had really any issues with these kind of resolving and probbing, even when our ops team shut down our DNS server and all of the database resolving didn't work anymore. Finagle just kept working because it cached all the addresses and just kept quiet until the DNS was there again. And they have circuit breakers and a lot of strategies to handle failure. And no matter how much we crashed our infrastructure, Finagle was pretty happy and running. So, and this is all hidden behind this few lines of code. So we've come so far. We've built a server and a sensor talking to Zookeeper, and now we go to the HTTP API. And who of you knows Finch? Okay, some of you. Yeah, Finch is a cool kid on the block. It's built on top of Finagle, and it's a very thin layer of pure functional basic blocks to build composable HTTP APIs. As you see in the first example, the Finagle API is pretty low level because it's very close to the protocol. So Finagle gives you some nice APIs to do that. And it gives you some simple and robust HTTP primitives, but they try to be as close to Finagle as possible to make the integration easy, but make the HTTP interface more usable. So so that Finch can work its magic, you need some imports. So first we import everything from Finagle, then we import an HTTP response classifier. We will see in a second how we use this. Then we import Finch Cersei, and the Cersei auto generation. And then everything just happens magically. So we define our endpoint. First of all, we define our JSON model that we want to return on our HTTP API. It's a simple case class, mean, which only contains the mean value. Then we define an endpoint. An endpoint is Finch's abstraction for an HTTP endpoint. So where you can send requests and get response to. And it gives you some nice helpers to define those. So in this case, we define an HTTP endpoint which responds to get responses on the URL weather/mean. And then you, in the block, you specify the actual implementation. So here we have, we spawned the temperature client as before. And now we're calling the mean method to get the mean temperature. And as a response, we get a future of double. We map over this double and return an OK response with the new model. And this already compiles and does the correct thing. So Finch handles future responses correctly, like RKGP or any other more modern framework does. And with this API definition, we can spawn a server. Again, choose a protocol, say we want to spawn a server, give it a label. And now you can see the with response classifier. And this is a nice example of Finagle trying to be as protocol agnostic as possible in every way, because Finagle doesn't know what protocol you're using or what is a failure in your protocol mean. So for HTTP, you probably want responses with 500 or 500 something to be marked as a failure. So Finagle can take actions if the server sends too many 500 responses, and maybe it takes it out of the load balancing or throttles request, but it doesn't know what a failure is. So you can give these response classifiers, which which enhances the server with the information what is a failure and what not. And then again, we just announce it. This time under /server/weather, so we can find it and bind it to an address. And if you remember the Thrift service, we had to create a new class with the new temperature service, Finagle service, and given a protocol API and stuff like this. Finch goes another way. If you have a type class that can create a service from HTTP request to HTTP response, you can simply call on your endpoint, so it's called API, the variable, you can call toService, and that's it. So you don't have to create a new class and wrap that again. So it's pretty straightforward. So a short recap, this was already a lot of information. So we wrote already 3 services that are that you can spawn on different machines that talk to each other, that react if something changes, if a new machine comes up or if a new machine comes down. We have a generic and shareable API definition with our Thrift service, so we can simply share either a jar with the compiled sources or the Thrift files if you like to, and simply use this service. But we have hard-coded service paths, so if I want to use another, if the service location changes, or I want to put it in another path, it's hard to do. I have to change all my services and restart all of them. And at the moment, we have no way of sending request metadata. So if everything we want to send via Thrift, we have to put it in the methods definition. So let's tackle the first problem. That's request routing. And you've already seen Dtabs on a few slides, and now I will give you some more information on what that actually is. Delegation tables are a way to resolve these paths. So as before, Finagle uses names to identify network locations, and a path is simply, well, it starts with a slash, and you have to interpret it so that it's, in the end, it's a resolved address that you can open a socket to. And the way delegation tables work is pretty straightforward. It's basically prefix substitution. So if we have a source prefix, then this prefix is replaced with the destination. And this is exactly what a delegation table entry looks like. So in this case, if we find /source, source will be replaced with destination. Otherwise, the rule is skipped, and it goes to the next rule. And delegation tables have some important properties. So, for instance, resolving with Dtabs must always terminate. So you have to make sure that in your delegation tables, when you define them, you don't put any recursion into, so that you, well, 2 rules call each other, and the resolving won't finish, and then, well, nothing works. The other property is Dtabs apply from bottom to top. So if you want to override entries, you simply append something to the list of delegation tables entries, and then you can override a more generic one at the top. And the other the most important property is that delegation tables are applied for each request, and this request and the delegation table is used for the entire request tree afterwards. So if you override something, then it will be applied to every following other request. And this is very useful. For instance, if you have canary instances, you start up one instance of a new service, and you delegate and you start your requests that you want to go through the canary system. And now all your requests don't hit your live system, but hit a special canary system. And so you can run the same instances of different services in multiple environments, and with the delegation tables, you can route specifically to the ones you want to. You can do debugging very easily. You can spawn local instances of a service and just be part of another whole system and just route one request to your local service. That's the important for you. So if I develop on a single service, and I can reuse the whole test infrastructure with Dtabs. So that's resolving work. This is a very small example. On the right, you see a kind of bigger delegation table, and then we start with this path. So we start from bottom to top. This is the first rule we can apply. We replace the S with S hash. Then we again go from bottom to top, and so on. So we apply always one rule after another until we end up with this kind of structure. So the dollar marks the ending of resolving a path, and the second, after the dollar, there's the implementation of your resolver. And this is actually what is used as well for the Zookeeper schema. So Twitter has a server set implementation, and this takes care of writing stuff to Zookeeper, these server sets, and resolving and getting them, and resolving services. So a server set basically kind of looks, I think it's JSON, and there's a host and an address in it. So it's pretty simple, but it works along with Zookeeper. And with this, you can resolve your path into a name bound which has an address. So what's the difference for clients? How do I create clients now if I can't use the schema? Well, it's only, first of all, you have to give some delegation tables. There are two kinds you can set. There is a base table. This is kind of awkward because dtab.base is somewhere a global variable, and you should set it at the beginning in your application, but nobody forbids you to set it anywhere else. So you have to be very disciplined in this case. But this delegation table base is used for all the requests. And then there is a local delegation table that you can set. You can specify a delegation table, and then you specify a code block where this delegation table is applied. So this is for single request overrides. And now the client everything is the same as I expect but the destination, it's now a simple path. So it's /s/temperature, and with delegation tables, the resolver will figure out how to look for the service now. So you have your resolving decoupled from your actual service instantiation, and you have this in a special place, and that's what delegation tables are good for. So how to override and Dtab in practice? So the most common way is probably using HTTP, and I found this just by reading the tests. You can give a special header which is called dtab -local, and you can specify a dtab if you like. So for API, in the example, there's a Finagle app as well, where you can switch the headers and route your requests depending on what button you clicked to different systems by just applying this header. So the second thing I want to talk about, which is very important and very useful, are request contexts. When you define your services in a Thrift IDL, you don't want to put all these meta information into your business logic. For instance, you don't want to specify the request timeout or the user authentication requests in every one of your methods that might or may use it. And this is what request contexts are for. So it's a request scoped state, such as authentication information or request deadlines. And Finagle takes care of persisting this and managing this state across threads, execution contexts, future pools, and even between client and server boundaries. So you have two implementations for this. A local one, which is per service. So it's inter-process context, in-process context, and you have a broadcast context, which will be sent over the wire. So you have to make sure that you don't send too many unrelated data, but you can choose between those. And it's passed implicitly. So you can access it anywhere in your Finagle service if it's available. To give a small example, we will implement a user authentication context. And we'll define it as a broadcast context. It looks pretty straightforward, so it's just a case class with a user ID. Currently at Gute Frage, we haven't seen this feature when we started 4 years ago. So we implemented our own request context, which we actually put in every method and check it, so which is kind of tedious. But I think the newer services got rid of that, and we're moving to more and more of these broadcast contexts. How does Finagle know where to look in your request for this context? You have to specify a key. The key first it takes a type parameter, which is the actual context. So in this case, it's a user context, and then you give it a string as an identifier. And best practice here is to use the fully qualified class name, so you don't get any naming collisions. And this is used by Finagle to look up your request context in the request. And then you have to implement marshalling. And again, Finagle here is very, very low level. So you have a buffer. I think this is a special implementation from Finagle. But basically, it's an array of bytes. And you have to specify how do you create this array of bytes from your user context. And the unmarshal is, well, try to get out a user context from some bytes. But again, you can, I think Thrift has a good support for buffering. So if you like, you can specify Thrift models and use the encoders and decoders for unmarshalling and marshalling. So if you're not so happy about implementing low-level byte stuff, you can use an encoder or decoder of your choice. So how do you use it? First of all, we have to provide the context. So in this case, we create a new user context. And this is, again, a pattern you see a lot more often. You have context broadcast.let. And, well, let specifies, in this case, the key you want to broadcast and the actual context. And then you have a block where this context is applied to all the requests you make. So you can, when you make 10 requests, all these 10 requests will contain this broadcast context. And this is also the same way the Dtabs local API works. So you have dtabs.local.let, and you give a dtab, and then this block afterwards, the dtab will be applied. And on the server side, where you want to read, or on the server side where you want to access this, you again use the user context key and current what you have, and this gives you an option of user context. So if you have a user context available, you can access it. Otherwise, well, you don't have any. So recap 2. So now we know how to route different requests with delegation tables, which is a very powerful feature, and decouples a lot of your service discovery into single delegation tables and not spread it into different services, and which may all do things differently. We can now separate request metadata from the business logic with request contexts and implement some cross-cutting functionality with that. So what are the next steps for us? We started, when I started doing this a year ago, we started more low-level documentation, the Finagle docs. I have to admit, I hadn't had time to work on these in the last few months, but it doesn't focus on the technical details and implementation details of Finagle, which the Finagle documentation really does well. It's if you're interested in all the details, you can read it, but it's not like, okay, how do I build a small system and plug things together? What choices do I have? So we started that covers these issues on how to get do I get started. And all the example code I showed today is in the repository as well. So there are very small patterns on how to implement a service, how to plug them together, what choices do you have, and also what features does Finagle have. And we try to extend these and write even more documentation on that, because it's also very important for us and for other companies. SoundCloud in Berlin, they're also doing a great job on writing blog posts on Finagle, but really try to give back something to the community. And of course, we want to leverage more of these Finagle features in our own code base. We discover more and more, and it's really nice. A lot of the issues we had in our own code base were already solved by Finagle, and we can just remove our own crappy custom code with battle-tested Finagle code. So these are some resources I really recommend checking these out if you're interested into. So the last one I just added today because I almost forgot. I wrote exactly this talk. I wrote as a Medium blog post, so you can read the slides or you can read the blog post. And yeah, there's really some nice information. The Finagle 101 is pretty good. It's also one of the core maintainers of Finch, and he really gives some great insights. So don't forget to rate what I just told you. And then thank you for your attention, for being here, and ready for questions.
Hello, I have something to ask you about some Finagle Thrift, and I know that Finagle Thrift is little different from Thrift, right? And I want to know why is that happen like this?
They use the Apache Thrift library, and at the moment we are upgrading our Finagle versions to a new one, and we're struggling again with the documentation because they're using a very old version of Thrift for the open source version. But there's a quite new version out for libthrift, and the Scrooge compiler recommends using the new version, while the Finagle documentation says you have to stay on the old version. But so far we have migrated to the newest version of Thrift, which is the one public available on Maven, and everything works so far. So I'm not sure. I think they're in some kind of transition for these kind of Thrift protocols.
But they say that Finagle Thrift is different from the Thrift, right?
It's a public available Java library, so I think it's the normal one. They have a special protocol, Thrift MUX, so where they implement muxing on the standard Thrift protocol. But I'm not so keen on the very details of Thrift. It's just one of the protocols we're using. So we also use the Redis client, and I think that we tried the MySQL client, but yeah, we're not so into the technical details of Thrift because we use Finagle for all of our services, and they work pretty well together, and that's what's available.
Thank you.
Cool. Then, thanks, and enjoy your lunch.